We will briefly discuss the air-sea interactions associated with monsoon intraseasonal oscillations or the intraseasonal variability in the monsoon domain briefly here. There are a couple of other chapters which go into more details but focus more on the MJOs. We will look at some of the ocean processes in that context. Here we will just look at the brief points made in this chapter for the sake of consistency. And the point made here is that the stronger wind speeds here at intraseasonal time scale correspond to heat loss from the ocean. So we are looking at time latitude section of 10 to 90 day filtered net heat flux, surface wind speed, sea surface temperatures, and CMAP precipitation for 2002 summer season averaged over this longitude band over the Bay of Bengal. And you can see it's showing northward propagation and showing a relation between wind speed and heat loss or heat gain from the ocean. Basically, when wind speeds increase, evaporative loss, latent heat loss increases, and you get intraseasonally negative anomalies. And there is a quadrature relation between the QNet or the net heat flux and sea surface temperatures. So sea surface temperatures warm by about 7 days when the net heat flux is reduced because of weaker wind speed, for example, and that means the atmosphere is largely controlling the sea surface temperature variability over the Bay of Bengal, and this is not the case for the other regions like the equatorial Indian Ocean, for example, where ocean dynamics also plays a role. And there is also a lag relation between sea surface temperatures and precipitation. Sea surface temperatures get organized to be warmer during the dry phase of the MISO, which typically means, so you can see cool SSTs are associated with precipitation, which means convection and precipitation increase wind speeds, take away the energy from the ocean, and SST cools. And then SST reorganizes into a warm patch during the dry phase of the rain, a convection associated with MISO, and so on. And this is argued to be able to be used for predicting the break periods by Harrison and Vecchi, or Vecchi and Harrison, Gabe Vecchi and Ed Harrison. But in our case here, the main point to be made is that the ocean does play a role in terms of organizing convection in terms of warm SSTs during the break period leading the precipitation by 7 to 10 days. But the general conclusion would be that the atmosphere is driving atmospheric intraseasonal variability through the heat flux is driving sea surface temperature variability, which means that the MISOs likely, at least the precipitation associated with the MISOs over the Bay of Bengal propagating along these latitudes and the longitude of 85 to 90 degree east are mostly internal variability of the atmosphere with feedback from the ocean, and this is confirmed by some of the modeling experiments made by Xiaohua Fu and Binwang Tim Lee and that group from Hawaii. This is showing the wave number frequency diagram for a coupled run and the difference between a air-sea coupled run and atmosphere forced with daily rainfall. They also look at SST forcing, where the daily variability has been removed and climatological SSTs are used, which makes the simulations even worse. And the point they make is that coupling is important for amplitude and propagation phase speed of the MISOs. But this question still very much remains kind of an open question. Most models do not do a proper representation of the MJOs or the northward propagating features. The other thing that's the other point made by Xiaohua is also very important. Looking at the relation between sea surface temperatures show anomalies with at interseasonal time scale shown here as the contours, and precipitation shown here as anomalies in gray shades. The main point would be that the sea surface temperature gets organized before precipitation happens. Okay, and when precipitation happens, sea surface temperatures cool, and then there are processes involved in reorganizing the sea surface temperatures. And this question has been looked at by many people in terms of whether the ocean dynamics is involved in organizing sea surface temperatures before the convection and after convection has cooled the sea surface temperatures, and so on. In the coupled model experiment and comparing to SST forced experiments, you can see that in the SST forced experiment, the sea surface temperature anomalies and precipitation anomalies occur simultaneously. So the relation, the phase lag lead relation between sea surface temperature and precipitation rates are not captured when you do SST forcing, so, which also indicates that air-sea interactions and coupling are likely important for interseasonal timescales. We will have to leave it at that because the question is looked at by several modeling experiments, and the general conclusion is that both MISOs and MJOs are stronger, and the phase relations between SST and convection amplitudes and phase speeds of the propagation are improved when coupling is represented. Air-sea interactions and ocean-atmosphere coupling are represented. But there are many questions in terms of the scale of the SST anomalies and scale of the atmospheric features. For example, MJO features are order 10,000 kilometers in zonal direction, whereas the sea surface temperature anomalies associated are typically of the order of 100 kilometers. And there are some arguments made by Zhao Lei in a paper that when the frequency and wave number of the upper atmosphere and the upper ocean and the lower atmosphere are similar to each other, then a strong coupling can happen and the atmosphere can feel the SST anomalies at a much smaller scale. This is not done for MISOs, but it is likely that the properties of the upper atmosphere and lower upper ocean and lower atmosphere play a critical role in terms of the coupling, but exactly how sea surface temperatures feed back to convection is not very well understood at these time scales. So just remember that air-sea interactions are important. Ocean-atmosphere coupling seems to be important for monsoon interseasonal oscillations, and we will return to some of these issues in the context of Madden-Julian oscillations as well later on. And we will look at the details of interseasonal variability in the ocean, as well as air-sea interactions associated with MJOs and MISOs later on. Okay.